Started. Welcome everyone. Thanks for joining us this evening. And this presentation is being put on by the Fallbrook Climate Action Team. We have a website as well, which is fallbrookclimateactionteam.org. And we do post some of our past presenters that we've had, as well as there's a lot of other good information on there. So feel free to check that out. And if you don't know who we are, we're a nonpartisan group of volunteers concerned about climate change. And what we do is bring you various topics on the last Tuesday of every month. So our next month will be, let me just get the date.
28th.
28th, thank you. I couldn't get my phone open fast enough. So it'll be September 28th. So look forward to joining you there again for our next topic. And before we get started, I'll just remind everyone that in order to keep a quiet line, we do like to keep everyone on mute and just ask that you hold your questions to the end. And then what we'll do is unmute you and we'll have a question and answer time. But in the meanwhile, so you don't have to write down your question or forget what your question was, go ahead and use the chat function, which is at the bottom. If you don't know how to access it, just scroll down, move your cursor down to the bottom, and you'll see an icon that says chat. Click on that. That'll open up a side box, and then you're able to type your question in there. And that way it'll store it, and we'll make sure to run through those towards the end of the presentation, as well as we'll unmute everyone and we can have more of a discussion. But this way we can give our guest speaker tonight a nice, clear, quiet line. So with that, tonight we do have Dr. David Hollenbach, and he is going to be discussing, can we nuke our way out of climate change? Big debate on nuclear, and is it clean? And even though you have the waste, how does that all play into it? And how is that going to affect our overall goals with trying to mitigate the climate change and the climate crisis? So Dr. Hollenbach has a PhD in theoretical physics from Cornell University and was a postdoctorate fellow at Harvard University. So some very good credentials there. I've got a fly buzzing around. He's also been a research scientist at the Space and Science Division at NASA Ames Research Center since 1980. So just a few years there at that facility. And we'll go ahead and turn it over to you, Dr. Hollenbach, and I don't know if you wanted to add anything else to the introduction there.
No, that's fine. That's fine. And I have to say that I did not pick this title, Nuking Us Out of Climate Change. That was, someone picked that for me. And I'm sorry to tell you that I'm not going to talk about nuking our way out of climate change. We should not nuke our way out of climate change. I can tell you that right away. We should solar and wind our way out of climate change. But what I'm going to talk about is solar and wind. The sun doesn't shine all the time, and the wind doesn't blow all the time. So even though we all want solar and wind to provide as much electricity as possible, there's got to be a third element that will fill the gap. And so the talk is about, should nuclear energy be that filler, or should it be something else? So I'm going to share screen now, I think. And let's see here. So that's really the idea in the talk is, should nuclear fill the gaps in solar and wind? Now, we're all kind of opposed to nuclear power. I've been opposed to nuclear power for many, many years, many decades. And we're opposed to it because of safety reasons. Things melt down. There's waste problems in storing the waste, especially storing the waste safely for hundreds of thousands of years. There's proliferation dangers, and there's costs. Nuclear power has gotten very expensive, and some of the plants are not even profitable anymore. So let's go back in history. Let's go back in history and let's go back to 1950. After the Second World War, there was a lot of optimism about nuclear power. People thought it could be the thing that was going to bring us cheap and abundant power for going way into the future, kind of an unlimited source. And as to kind of show you the enthusiasm, here's a Gilbert used to make chemistry and all kinds of sets for kids. And they made an atomic energy lab for children back in 1950, which had Geiger counters and radioactive material and cloud chambers and so forth. It cost $50 in 1950, which, what is it, about $1,000 now. As you can imagine, this was not a very successful commercial venture. They only sold a couple hundred sets and then they took it off the market. It's probably worth $1 million now as a collector's item. But there was enormous enthusiasm in the kind of general community that nuclear power might be in our future. But of course, the military was also interested in nuclear power in the 50s, not only to make nuclear weapons, but to drive ships. And Admiral Hyman Rickover was a big pusher of developing a nuclear reactor that would provide the electricity that would drive a submarine. And it was because of his push that we have the nuclear reactors that are practically in all nuclear power plants today. It's a water-cooled, uranium-based nuclear reactor. But it was designed for a submarine. And of course, the Nautilus was launched in 1954. At the same time in the 50s, at Oak Ridge, Tennessee, there was a guy named Alvin Weinberg who was developing what he thought would be a better type of a power plant, nuclear power plant that would be safer and would be better suited for civilian use. But the military, as usual, won out. And so commercial plants started. And the first US power plant, nuclear power plant, commercial plant, was in Dresden. It's near Joliet, Illinois. And it opened up in 1960. And there's a little family Hollenbach story here. In 1957, we had just gotten a 24-inch black and white TV. And my aunt, Mary Fran, called us one night and said, Uncle Fred's gonna be on TV, Fred Hollenbach, my uncle. And so Sunday night, he's gonna be on. So Sunday night was Ed Sullivan, for those of you who are old enough to remember. I'm one of the few. But there was Ed Sullivan. After Ed Sullivan was the General Electric Theater. And in the commercial for the General Electric Theater, my Uncle Fred, who was a nuclear engineer who helped building this plant, appeared. So that was the first Hollenbach appearance on television. So, well, the 60s, the 70s came, people started to get, I was in college in the 60s and 70s. And we started to get very nervous about nuclear power for various safety reasons, waste reasons, and so on. And that sort of culminated in the meltdown of 3 Mile Island in Pennsylvania in 1979. And here's a picture of Jimmy Carter touring the plant in 79. And there's a little sort of a curious family story here too. My cousin Art was an environmental scientist, and he helped elect Jimmy Carter. He was a big person in the Carter campaign. And so Carter appointed him to the 3 Mile Island Commission to see what happened. And so by this point, we're really against nuclear power, you know. But then we started to get more and more aware of climate change. And so with climate change came a time perhaps to reflect on, should we look at nuclear power again, and should we actually include nuclear power, which doesn't create any greenhouse gases in the mix. So where does our greenhouse gases come from in this country? Well, this pie chart shows that 27% of the fossil fuels are burned to create electricity. 28% are burned on our cars and trucks. 22% goes to industry for to heat and to drive the industrial processes. 12% goes to heating and providing energy for our homes, and so on. So that's where we are generating these unbelievable amounts of carbon dioxide that's going into the atmosphere and heating up the climate. So what's the path to going to zero carbon then? Well, the path is an electric world. We've got to turn the entire world electric. And to do that without creating any carbon, we have to produce the electricity from something other than burning fossil fuels. We got to produce the electricity by solar, by wind, by nuclear, by hydro, by things that don't produce carbon dioxide. And if we do, then that same pie chart, the electricity is not produced by carbon, but in addition, we produce more of it, and we use the electricity to charge the batteries in our cars or trucks. We use electricity to drive industry. We use electricity to heat our homes and to power our homes. And we basically eliminate all the carbon dioxide that is being produced right now. So that's the path, is producing. So how do we produce electricity right now, or in the last 10 years, let's say? Well, not say from 2007 until 2017. Well, in 2007, you can see that here's coal, still 48%, natural gas, 22%. They add up to 70%. 70% of our electricity came from burning fossil fuels and putting carbon dioxide into the atmosphere. Then if you look at wind and solar, that's this other renewables. It was a very tiny amount in 2007. Hydro was bigger, but the main thing that was producing electricity without CO2 was nuclear in 2007. Now let's go 10 years in the future into 2017, and you can see that solar and wind has now gotten from 3% up to 10%. So there's been an enormous increase in the amount of electricity produced by solar and wind. And it's cut into the fossil fuels, using fossil fuels. Nuclear stayed about the same, but the other thing that's happened, as you can see, is that we're burning more natural gas now and less coal. The two of them, natural gas and coal, still add up to 62%. So we're still burning a lot of fossil fuels due to electricity, but we're burning a lot less coal. Coal does produce more CO2 than natural gas. So it's better to do natural gas, but it's not ideal. We don't want to burn anything. So here, now let's go 10 years even into the future, from 2017, or even 18 years into the future. This is a study done by a group that I belong to called the Union of Concerned Scientists, which is sort of a left-wing group that has been involved in trying to reduce nuclear weapons in the world, trying to reduce proliferation, trying to make things safer in various ways. And so they did a study. This is that same chart of where we're generating electricity in 2017. You can see coal and gas, more than half is being coal and gas, and there's nuclear. And then you can see this little tiny yellow here is solar and wind. And the Union of Concerned Scientists put forward a fairly ambitious goal of the next 18 years that involved incentives to get off of carbon, and that provided incentives to go to use things other than carbon. And this is what they came up with in a somewhat optimistic, perhaps, scenario. You can see that they've increased solar tremendously from 2017, and they've increased wind, which is the purple, enormously in this projection of what we should do. And wind is, hydro is about the same. Nuclear is somewhat reduced, and then basically eliminating all the coal almost, and then having, but still you'll see that there's maybe 30–40% of natural gas that still is going to be being burned. So we'll still be creating greenhouse gas, but at a much reduced, perhaps half the level that we are now. But one of the points of this that might surprise you, because the Union of Concerned Scientists is a fairly progressive group, is that they actually pleaded in this, oops, I'm sorry, I'm gonna do that. They pleaded that even though nuclear plants today, many of them are unprofitable. And so there's been a move afoot to just decommission all the nuclear power plants that are unprofitable. They actually, in this report, argued, no, we should keep those power plants going, even if it requires government subsidies, at least the safe plants. We should keep them going. The reason that it's decreased here is that they were eliminating some of what they considered the more dangerous plants. But they actually said, even if they're not profitable, they're not producing carbon dioxide. And if we decommission them, what's going to take its place is going to be natural gas. And so we'll be burning more greenhouse gases into the atmosphere if we decommission them too rapidly. So it was actually a plea to keep existing plants going. So now let's go to 2050, or think about the future, 2050. As you probably know, the goals of many of us is that we get to zero carbon by 2050, or close to zero carbon. And so let's just look at this, what I call the electricity gap. And this is an example from California. And what's plotted here is power generated as a function of time, and just over a few days, 5 days in June in California. And this was in a region where there was solar and wind available in this community. And you can see the problem with solar and wind. So here's the sun. The sun comes up. I hope you see my arrow. I think you do. The sun comes up in the middle of the day, you get a lot of solar power, but then the sun goes down and then you get none. And then the next morning, the sun comes up again and then it goes down. And this is what happens with solar power. So there's no power at night. Now, wind can take up some of that, but of course the wind is unpredictable. And so the wind is kind of going up and down. Sometimes, sorry. What's happening? Hold on. Try that. Okay, that works. So the wind can pick up a little bit of this, but what they're doing now in California, of course, is burning gas to fill the gaps. So when the sun goes down and there's a lot of high peak of use around 6 p.m. to 8 p.m., they're burning gas to create electricity, and it creates greenhouse gas. And the nuclear they've got available in this community just provides this steady amount. And current nuclear plants are very hard to turn on and off very quickly. So they aren't that good at, like, just all of a sudden you turn them on at 5 o'clock and you turn them off in the morning. But this new generation that I'm going to talk about does have the capability of being turned on and off relatively rapidly. So there is the potential with this new generation of nuclear power to actually fulfill these gaps when we need it, when the sun doesn't shine and the wind doesn't blow. So, this. So this talk is going to talk a little bit about this, can it fill the gap? And filling the gap, there's other possibilities of filling the gap. There's storage with batteries, and I'm going to talk a little bit about this right at the end of my talk. There's using gas, burning gas to create electric power, but then sequestering the gas, the carbon dioxide that's produced, and just pumping it into the ground. I am very skeptical that this can be done on a large scale. And so I'm not even going to talk about it, but I am going to kind of compare storage and nuclear. Nuclear could be another possibility. So, and I'll say, I mean, I know that we're all prejudiced against nuclear, but if you look, the Intergovernmental Panel on Climate Change, which just issued a report, includes nuclear and talks about nuclear as a something that doesn't produce carbon dioxide. It's recommended for research and development in various, by the Biden plan and Democratic House panel and this Democratic Senate panel. So there is recommendations, and they all call out these what they call Generation 4 reactors. And at the end, if you want to ask, I can tell you what Generation 1, 2, and 3 are. But the ones for the future are called Generation 4. They're not operational yet. There's not even prototypes of many of them. So I need to break a bit for science as a key to understanding Generation 4. Of course, the main thing about nuclear power is that per pound of fuel, you generate 1 million times more electricity. That for this, just take a power plant, say you have a power plant that produces a big power plant that produces electricity. It might put, say, a gigaton of carbon dioxide into the atmosphere, 1 billion tons. That same power plant for a year would use maybe 1,000 tons of uranium. So it would be 1 million times less waste. It's just that it's solid waste as opposed to gas that goes into the atmosphere. That solid waste, it's pretty dense and heavy. You could fit it in a building, actually. I don't know, sometimes it works, sometimes it doesn't. Let's do this. So where does this energy come from? And the basic physics is that you take a fissile atom like uranium. This is 235 as an isotope, but you don't have to even know what an isotope is. Anyway, this uranium isotope, if you hit it with a neutron, it will split apart into 2 other atoms. In this case, you have a krypton and barium, barium. but it might be xenon, it might be strontium, it might be iodine, it could be anything. They split apart into two atoms, but it gives off an enormous amount of energy, heat energy. And then you use the heat to boil water, and then you use the water, the steam drives an electric turbine. And it's a very simple way of producing electricity, but of course it has its drawbacks. And what keeps it going, the thing that's kind of amazing is that if you just had one of these uranium atoms in your hand, you'd have to wait 1 billion years for it to actually radioactively decay. 1 billion years. But if you hit it with a neutron, you can get it to split apart in a matter of seconds, or you can induce it to just much more rapidly kind of become radioactive and split apart. And what happens when they split apart is you create more neutrons. And so these neutrons then can hit other uranium atoms and cause them to split apart. And so you get a chain reaction going. It's like a domino effect where one domino drops and they all start dropping. And so that's the idea. You get this thing, and then that produces a lot of heat, and you use that heat to drive your source. Now the fuel rods for current nuclear reactors, what do they look like? Well, here's the fuel. This is the uranium itself, and they're in these sugar cube sized pellets. And something that people don't realize is that this could be a pellet of plutonium or uranium, and you could hold it in your hand and it would be safe. But what is not safe is if atoms of the uranium or plutonium get into your water supply, or if you breathe them. If there's any kind of a fire, or if it gets in the air and you breathe it, it's incredibly dangerous. But so these things are placed into these little sugar-sized cubes, into these cylindrical rods that are 2 to 6 feet long, and they're bundled together. And by putting all this uranium close together, you can get this chain reaction going that I mentioned. So the problem, of course, as everybody is aware of, is waste, one of the big problems. And so currently we have about 60 nuclear power plants in the country producing this 22% of our electricity. They have about 90, 100 reactors in them. Some of the power plants have 2 reactors. But this is how they work. You mine the uranium. Uranium comes out in these 2 isotopes, the slightly different forms of uranium. It's the U-235 isotope, that's the one that is fissile and which creates the energy. The U-238 is relatively inert, although I'll talk about it in a minute. And these rods are 96% of this kind of inert uranium and 4% of this active uranium. And that's enriched. Naturally, you have much less than 1% of this active uranium. So you enrich it. So then you make these rods. You put the rods in this reactor, and the heat generates steam and it drives a reactor. But now what happens inside the rod is that as the U-235 splits apart, it creates 2 things. Well, it creates 2 things. It creates fission products, which are splitting apart into 2 atoms. And so some of these atoms that splits apart are perfectly harmless, but some of them are radioactive, and they're much more radioactive. Remember I said if you held a uranium atom in your hand, you'd have to wait 1 billion years for it to decay. Some of the stuff, after it splits apart, it creates radioactive things that will decay in a year or less. And they're very radioactive. And so these rods, because of these fission products that are very radioactive, they are hot. So, I mean, literally warm to the touch. And so they put them in holding ponds at first just to cool them off. The other thing that happens is that the uranium, the neutrons that are present inside the reactor hit the 238, and it turns this sort of inert U-238 into plutonium. And plutonium is the thing that we all worry about in terms of nuclear waste, because it has to be stored for 100,000 years. It has a long half-life of decaying, and it's extremely poisonous, and it can burn and create smoke of plutonium particles that you can breathe, or it can get into your water supply. And it's really the plutonium that's one of the key things that is really horrible about nuclear power. Okay, so but now one of the concepts for the new generation is basically that we use the uranium much more efficiently, and that we basically use it all up, so there isn't much waste left. And one way to do that, remember that 95% of the rod was 238. But if you hit neutrons on the U-238, it does turn into plutonium. But if you keep that plutonium splitting apart, you just keep it splitting apart, you can kind of use it up. Or you can take what's called a fertile atom like thorium, which is a very safe thing to handle, hit it with a neutron, and it becomes U-233, uranium-233, and then that leads to energy. And it doesn't produce plutonium in the process. But there are some caveats to that if later you can ask me about if you want. But the goal basically is to use up the fuel and leave little or no plutonium to create much less waste that you have to deal with, and much safer waste. If it's just fission products, you'll need to only store them for like 100 years or a few hundred years. And that maybe is much more doable. So that's the key concept. So for these generation 4, the idea is, first of all, you don't want them as expensive as these nuclear power plants are. Secondly, you want them ready quickly. If you want to do anything about climate change, you want them ready maybe by 2040. And so the design is a simpler and small modular reactors. They call them SMRs, small modular. They're much smaller reactors than are currently being used, but the idea is that they'll be modular so that if you need more energy and more power in a city, you just put several of them together. And they'll have fast turn on and turn off so that we can fill this gap in solar and wind. And because they're small modular, you kind of assembly line produce them, and that helps them to be cheaper. And these, I must say, are goals. This does not mean that this is something that's going to happen. These are the goals. The goal is the waste is much more efficiently use up the fuel and use less fuel, and you have 100 times less waste, and you will only need to store it for 300 years if you don't produce plutonium. And then for safety, the goal is, and they're starting to do this in some of the nuclear reactors, passive safety, which means there doesn't have to be a human pushing a button to dump coolant on it. If you're getting a meltdown, you don't have to have a human there to do something. Or you don't even have to have some sort of electrical computerized thing that senses it and sends some message to open a valve or something. You don't need any of that. It can be completely passively quench itself and not go into meltdown. And the fourth thing is to reduce proliferation risk. So this is the size of a prototype of one of these things. You can see they're not real big. They're about the size maybe of a railroad car. And I'm going to give you an example of one. There are many different concepts for these 4th generation, but I'm just going to give you one example, and that's the molten salt reactor. Oddly enough, it was the reactor that in the 50s, Alan Weinberg at Oak Ridge actually produced a prototype that actually generated electricity and actually worked using this type of technology. What you do is you put the uranium or the thorium and you have it in a salt, and you have that salt heated up to maybe 1,000 degrees Fahrenheit, very hot, and it melts, the salt melts. So you got this molten liquid salt, and it's got the radioactivity, the uranium, the fuel in it. And that starts, and then you get this chain reaction going, and so it self-sustains the heat. So you don't have to add heat. It stays molten just because the nuclear reaction is actually creating the heat. And then that's it. That's all you need to do. You have this hot liquid then that's going to stay hot due to the reactions, and you then pipe it into a vessel that has water in it, and it's very, very hot. And so it boils the water. It's like a little electric pad. The water creates steam. Steam drives the turbine. Turbine drives electricity. Now, the thing that I forgot to maybe mention is that one of the reasons we get so much waste in these rods and we don't burn up more is that in the rods, when you have fission, you create contaminants, and like xenon gas is created. As uranium splits apart, you get a xenon atom every now and then. Xenon absorbs neutrons. It absorbs them so efficiently, it stops the chain reaction. So as soon as you've created a little xenon, you can't use the rod anymore. You got to just throw it away. And these nuclear power plants maybe go through 50,000 rods a year. So you build up a lot of waste, and there's just a lot of uranium and plutonium and things left in the rod. But here, what you do is you remove those impurities. You recycle. You take fuel, you put it into a reprocessing module. You get rid of the contaminants, and you put the fresh and reprocessed fuel back in. And that way, you can use the contaminants don't stop you, and you can keep using it up and using it up. That's the idea. And then, as for a passive safety, they have a little freeze valve here, which is made of a salt that melts at a higher temperature. And so if this thing starts to try to melt down, if it starts to overheat, what happens is that this solid salt here melts, and then it just drains this tank into this huge holding tank, which spreads out the stuff, and it stops the chain reaction. And so it then stops it without any human intervention, without any electricity, with nothing. It's passive. So that all sounds great. But of course, there's always a but. And here are the buts, or some of them. So this group that I belong to, the Union of Concerned Scientists, went through all these different concepts for these Generation 4 nuclear reactors. And they went through this molten salt reactor. And what they found was that this particular one got the following grades. On waste, it was significantly better. It did burn out more fuel. It did create less waste. So that was good. But on the other two, safety and proliferation, significantly worse. And this is worse than current nuclear reactors. And I'll just go back, if I can, just for a second to tell you what they discovered, why it was not as good as it looked. For safety, for one thing, this salt might get clogged, and it might not drain the tank fast enough, and you could get an overheating. That was one thing. The other safety is that you produce radioactive gas in this. Remember, I said xenon is produced, but also cesium in a gaseous form is produced. That gas gets released in here, and you've got to collect it, and it's radioactive. And the cesium stays radioactive for 30 years. So you have to somehow store it for 30 years and collect it. And there's a danger of it escaping, and it's very, very dangerous to get out. It adheres to soil, and it can get into the food supply. It's one of the things that was really bad at Fukushima. And the other thing was proliferation. If you have a reprocessing plant here, it turns out those things are great for using to make bombs and things with. So you don't, I mean, our current reactors don't have such a reprocessing plant, but this does. So that's why they gave it these grades. And the additional, and they went through all the different concepts, and it came to the sort of similar conclusions. I mean, some of them were better in some things, but worse in other things, blah, blah, blah. But none of them looked as ideal as they sort of sound on paper. And the other thing they pointed out is that the timing is not good, that it takes decades to get these things really commercially in use. And we have to get the carbon dioxide down by 2050. I mean, there is time pressure on us now. You know, we have dilly-dallied long enough. And so their thinking is that there's not going to be enough time to get these Generation 4s, even if they could get all the kinks out. So there's this kind of a negative. Now, so what's the future of nuclear power? Well, what Bill Gates has invested $1 billion of his own dollars. Of course, that's probably chump change to Bill Gates, but he's invested $1 billion of his own money in one of these Generation 4 ideas. And he says, without this next generation of nuclear will go to zero. Well, maybe it should go to zero. The Union of Concerned Scientists actually leave a little bit of doubt, because they, you know, if you could put the good qualities of a number of these Generation 4 concepts together, you might be able to get something decent. But there are maybe alternatives. So I want to just briefly, I just have 2 slides to show you something about battery storage. So here's a picture of the largest combination of wind and battery that is operating today in the world in Australia. And so you have the wind energy whenever the wind blows, but you store up excess wind energy in batteries. These are Tesla batteries. So another billionaire, Elon Musk, is betting on batteries for this solution, because then you can, when the wind's not blowing, you can tap off the battery storage. And this is actually in operation. So there's been a study of batteries done at MIT, a lot of the studies led by a woman named Jessica Transit. And they looked at 20 years of weather in 4 states, quite different states. And it turns out that even without storage or nuclear, wind and solar could produce of order of 50, 75% of people's power. But you need something for the rest. And their claim is that batteries could get up to 95% by 2030. they're looking at, and they studied it economically too, the fact that battery prices are coming down very rapidly. Now you might think that lithium ion batteries, which you probably, that's what they use in cars, that's what they use in, for your computers and for your iPhones and everything. But lithium ion is not the ideal choice if you want utility scale, because what lithium ion is good for is storing a lot of energy in a small, relatively light battery. But if you're storing utility scale, you don't care if it's small and you don't care if it's light. You just want to store a lot. And you want it cheap because you got to store so much. And so it might be that some other types, and they talk about other types of batteries. But the thing that drove it, why couldn't we get 100%? Well, in a way we could get 100% using storage, but that extra 5% comes at a tremendous cost, it's a financial cost, not safety cost. And the reason is that they found in this study of weather that there are periods where the wind does not blow and the sun does not shine for like 20 days, okay? And so you would need batteries to be able to produce electricity for a huge community, for 20 days. Now, but if you only have batteries for 2 days, that'll take care of you 95% of the time. So you can kind of see the cost thing going here. You can, for a certain price, you get up to 95%. That is if you've got 2 days worth of storage. But if you want to get the other 5%, you got to have 20 days of storage. You need 10 times as many batteries. It will cost you 10 times as much. And you'll only use those batteries maybe 2 or 3 weeks out of every year or every 2 years. So there's the question of, should something else be filling in that 5%? Because you just are going to have so many batteries for these kind of emergency situations. So that's the summary. My talk now is, I'm going to summarize, which is, should nuclear help solve the climate crisis? It's been recommended that it be studied by various groups. Demonstration plants cost about $2 billion if we want to make progress on any of these Generation 4 ideas. Should we fund several of these plants? The climate crisis is urgent. I mean, should we adopt a shotgun approach and develop and research all our alternatives, including nuclear? Or is nuclear a Pandora box and storage or something else the answer? So I'll leave that to your questions, and thank you very much. It's been fun talking to you. I guess I have to unshare.
Stop share, please. Yeah.
I'll stop share. There we go.
That was a great talk, Dave.
You're muted.
No, you're not muted. I heard you.
Oh, okay.
I didn't join separately. We didn't want feedback. It was a wonderful talk.
Okay, well, thanks.
I thought it was fascinating. I like the way.
Very well. We do have a question here. Are the electrical need projections based on current use or increased use with the increase in electric cars, electric cooking, etc.?
No, that's exactly a good point. That as I said in that one graph, the way to get to where we reduce our carbon dioxide emissions into the atmosphere really, really significantly is that we basically have to electrify everything. And one of them is cars, like you just mentioned. And that means we're going to have to produce more electricity, because now we're going to be using electricity not only for the things we're doing now, but we're going to be using it for cars, for trucks, for industry, much more use in the home than, say, gas appliances, for example, or gas heating or fossil fuel heating of homes. So yeah, there's going to be much more demand. And so these projections take into account some of that increased demand. Yeah, now energy efficiency is another place to sort of save on fossil fuel. And in one of those graphs, there was this little box about how much we could save by really getting more energy efficient. It was the graph in 2035. They had increased the energy efficiency. And we're making big strides on that. I mean, there are a number of ways that we're using less electricity. I mean, we now get these light bulbs that only take 6 watts instead of 60 watts or something. I mean, that's a factor of 10 less, so, and, refrigerators are more efficient. they're making houses more insulated so that they're more efficient double pane glass, blah, blah, blah. So that's another way to sort of, so we don't need to maybe triple our electric production, but maybe we can increase it some, but not as much due to efficiency.
And a follow-up to that, does the electrical availability take into account reductions in hydropower due to reduced water supply?
Right. That's a really good point. And
Yeah.
but as you saw probably in all those graphs, hydro was only providing, even in the future projections, only providing on the order of 6-7% of the electricity. So, you know, it would be a small, if we start to get less power, suppose say in Colorado, they get less power because of, they don't have as much hydroelectric, or in Nevada is a better example, Las Vegas or something. But well, then what we'd have to do for that extra 6 or 7% is just put 6 or 7% more solar panels up and things like that. I mean, we'd have to increase slightly, but it wouldn't be a huge perturbation because hydro doesn't produce all that much even now. One of the ways to store, you probably heard, and they do this in California. They actually, Cindy and I and Pat and Dottie used to drive over, what was it called? The Checo Pass. And there's a big reservoir there. And what they do is that when they've got power in the daytime, they pump water up into that reservoir. And then at night, they let the water drain down and run hydro. And so it's a way of using, say, solar and wind power and storing it, not with a battery, but with hydro. But you can't do that everywhere. You need, you know, hills and places to pump the water. And, you know, so you need batteries probably to do the overall solution.
Interesting. Okay. And questions are rolling in here. What about hydrogen?
Yeah. Well, the hydrogen can be used as a storage possibility, yes. And I think that maybe that was the gist of the question. And then what you do is you use the excess energy you're getting from solar and wind, say when the wind's blowing and the sun's shining, to create hydrogen. If you're creating pure hydrogen, one way to do it is just to split hydrogen out of water. So you get hydrogen and oxygen. And so you use the energy, it takes energy to split water into hydrogen and oxygen, but you use that solar and wind energy during the day, say, or the solar energy during the day to create this hydrogen. Then at night, you can burn the hydrogen, and then by burning it, you only create water. It doesn't create a greenhouse gas. I mean, it just creates water vapor. And so Pat Casson can answer, I mean, there's that very subtle question. Water is a greenhouse gas in a sense, but really what drives our climate change is carbon dioxide and methane. Water is pretty much regulated by the seas and by evaporation and condensation and rain and so forth. And so adding a little water by burning hydrogen doesn't do anything really. It's clean.
But it sounds like that wasn't a major part of the plan.
Well, no, it takes a lot of energy to split it apart, and then you have to store the hydrogen. And can you store in large enough quantities? I don't know all the answers because I haven't studied storage as much. There's all sorts of techniques for storage. One of them being used is, I'm sorry to go off on tangents, I get going sometimes, but you can pump air into the ground and you get it under very high pressure in caves under the ground. And then you, at night, or say when you need the power, that high pressure air is used to drive turbines. It just blows turbines. And so there's all sorts of fancy ways to store. But I personally, and I think a lot of people think that it's going to be batteries in general that will be the main storage solution. Although these other techniques will be used in various places depending on, like hydro.
And we had a clarification that the question was really about hydrogen powered cars. I think Iceland has hydrogen buses, if I remember.
Hey, Pat, I'm getting out of my league, but I bet you know something about this. Pat Casson, you want to? Pat is also a friend of mine and even more of an expert on climate change than I am by far.
I think you said it right, Dave. It's a good storage facility, but you're not really generating any hydrogen any energy from hydrogen, since you have to use energy to get it.
But what
So,
about the hydrogen cars? That's what they were asking about, hydrogen fuel.
yeah, well, Toyota is making hydrogen cell cars, and there's technological issues. In principle, it's fine and it'll work, but it's the usual technological issues. It's hard to store. It's leaky, but Toyota's building cars that are hydrogen cell cars. So if the engineering aspects can be solved, it will probably work. But again, you need a whole infrastructure. You have to be able to pull up and pump hydrogen into your car or buy a canister or something like that. So it's economics and it's technology. The physics is there. It's a good energy storage medium. Okay. I'm not sure that answers the question, but.
Right.
Very good. Very good. A couple more questions. Where is the greatest impetus or investment coming from to move us forward?
Well, it's the Department of Energy that funds, for example, this nuclear research, but it also funds things in energy efficiency, all sorts of things. So that's a big impetus. At the federal level, I mean, at the something that Congress could do, it would be, things like subsidies. Right now, we subsidize fossil fuels. We could stop doing that. We could subsidize solar and wind more. So there's that could be done that could make a big difference. But in terms of research on new techniques, even fusion is being, it's being funded mostly by the Department of Energy. And the way that often works is that you write grants to the Department of Energy. So corporations or huge industries will write grants. I mean, some of it is being done by venture capitalists. I mean, some of this work on the Generation 4 nuclear reactors has attracted a lot of interest in venture capitalists, including Bill Gates, as I said, put $1 billion of his own dollars in it. And so there is just private money going into trying to develop something that might work and be cleaner and safer and so forth. Mm-hmm. So there's a variety of things, but I would say Department of Energy is probably the main answer.
Okay. Are there other countries that are making greater strides in these developments, or at least in the research? Or are we leading the way?
Well, we should lead the way. No, it's being, I mean, China is putting a lot of China's actually concerned about climate change and has been actually putting more government dollars into solar and wind and things and nuclear. One of the funny stories about poor Bill Gates, not that he's poor, he's rich, but Bill Gates had this idea for a Generation 4 reactor, or he didn't have the idea, but he got interested in this idea. And a company was called TerraPower. And they had this idea for a Generation 4 reactor, and it cost billions, maybe $2 billion to build a prototype. But he had the agreement of the Chinese government that the Chinese government and Bill Gates and TerraPower were going to do this prototype, and they were going to do it in China. And then Trump went hot and cold on a lot of things. But first, he was real friendly with China, but then he got really pissed at China and unhappy with China. And during the unhappy period, he basically put a kibosh on this collaboration between U.S. company and Chinese company. So that never happened. So now they're trying to get money here in the United States to develop this idea. But no, China is really pushing forward. India obviously has 1 billion people or whatever, and has a tremendous need to get off fossil fuel. And they've been putting money into nuclear power and so there's been developments in a number of countries. Of course, Europe has incredible scientists, and so they're all working on. I guess the question was specific to nuclear, and yeah, there's just a whole bevy of countries that have been putting some research and energy into looking into nuclear.
Okay, what about electromagnetism for power production? Any efforts?
Well, I mean, I'm not sure where that question comes from. It's the power that creates the electromagnetism, not vice versa. I mean, because what electromagnetism is electric currents and magnetic fields. And the way you produce magnetic fields is via electric currents. But how do you get electric currents? You got to have electric power plant, you know. So it's not like electromagnetism can create power. It's like power can create an electromagnetic field. I mean, I guess I don't quite understand the question.
I'm reading it here. Maybe it was just a way of amplifying the power production, but it sounds like there's not a lot of effort to develop.
Yeah, energy is sort of conserved. I mean, you can't get energy from no energy, and so
Yeah, it can't be created nor destroyed.
yeah, well, in a funny way, nuclear power is taking matter and turning it into energy. But yeah, I mean, you can't bootstrap your way. I mean, you need a fundamental source of the energy. That fundamental source can be fusion, can be fission, which is the nuclear power plants that we're talking about today. Fusion seems to be very far off in the future. It's a different thing than fission. And I didn't have time to go into fusion, but you can get it from that, or you can get it from burning things, you know, because you're basically taking stored sun energy. You know, coal is basically stored sun energy because, you know, plants absorb sunlight and, you know, they turn carbon dioxide, which has already been burned, but they turned it back into these hydrocarbons that can be burned. And it's basically storing that sunlight energy. And then when we burn it, it releases the sunlight energy. So
Okay.
that's what fossil fuels are. They're just stored sun energy. But the problem is that they've been stored over millions of years, the coal and the gas, you know, been under the ground, stored. They've been slowly being stored up over millions of years. And now to burn them in like 100 years is creating a devastation in the atmosphere. You know?
Yeah. And we have another couple questions. Next one, you meant, this is a show off. This is my husband showing off. You mentioned breeder reactors. What about the new ADS, or accelerated driven system, which converts thorium into U-233, clean, low waste? Any progress in this reactor?
Okay, let me explain.
No,
Where did that come from, bud?
I'll explain. I read an article a couple weeks ago and I sent it to our team. It was about the ADS. I thought maybe you might know something about it. But you mentioned the breeder reactor. I got really excited because that was what the article was about. This ADS meaning accelerator driven system. It takes thorium, which you mentioned, converts thorium into fissile uranium-233. It's really safe. It's no emissions, no radioactive waste, and there's plenty of thorium. Like they say 1 ton of thorium could provide enough energy for 3 million ton, replace 3 million tons of coal. So I don't know, it was a new article. I never heard of this machine, but have you heard of it? And
well, yeah, in fact, you know, there was a book out. In fact, I think Pat Cassins on this call recommended this book to me, or maybe mentioned it to me at one point. I think it was somewhat sensationalized, but it was about using thorium because, and I mentioned it in my talk, because thorium is a safe element to handle. In fact, it was used in toothpaste in Germany, and I think it's used in Coleman lanterns for the kind of a wick on a Coleman lantern. They have thorium in it. Anyway, it's safe. But if you hit it with a neutron, it turns into U-233, and U-233 is fissile, which means it can go do a chain reaction. And that chain doesn't produce plutonium. But however, there's a number of things that are worrisome about it. One is that a step along the way is the thorium produces something called protactium or something like that. It's another element before it becomes U-233. And you have to keep removing that protactium to keep this thing going, and that then is a proliferation problem, because if you're storing this protactium, you can make pure U-233 out of it, and you can make bombs out of U-233, and so there are proliferation problems. But in addition, in order to get this reaction, the thorium, going, usually you need to use some just normal uranium to get the neutrons that you need to get this chain reaction going. You need to kind of goose start it to get the thorium to turn into U-233. And that uranium then produces plutonium and other ways too. So in a way, plutonium gets involved, even though the direct reaction doesn't create plutonium. So I think that a lot of these generation 4 do mention using thorium as a potential fuel, but they don't see it as that much superior to other types of fuel. I've seen thorium mentioned as well. We can put thorium in this reactor, or we can put uranium, either one, and it'll work. I was really enthusiastic. I was so enthusiastic about thorium when I first read this book that I started looking into investing. You know, I have a little money to invest in. I'm gonna invest in thorium. Yeah. I'm glad I didn't, because it hasn't really panned out to.
Okay.
And then we have one final question, probably a good one to end the night on. What excites you most as you look at what seems most promising at this point in time?
Good question.
Well, I mean, I probably showed my prejudices. I think that it's a combination of solar, wind, and storage, and it's very exciting to see. Well, one thing we've all seen is how cheap solar panels, you know, and the cost of producing electricity with solar panels has gone way, way down over the years as we mass produce solar panels. Same thing, wind energy has gotten really cheap. So now it's totally competitive, if not cheaper, than burning coal or burning fossil fuels. You know, so that's been exciting, and so that's one of the causes of this big growth in solar and wind. But the other thing is that battery prices are going way down. I saw this chart in preparing this talk of lithium-ion batteries, and in the old days when they first got these lithium-ion batteries, I think they said that if you bought a Tesla car and they put one of those old batteries in, it would cost like $1 million because the battery would cost that much. But the batteries have gone, now the batteries in a Tesla car cost like $6,000. I mean, they've gone from $1 million to $6,000 in a matter of, you know, years. And so the price of batteries is going down, which means storage is getting more and more feasible to store electricity on a large scale. So that also excites me.
David, you mentioned storage, but are you talking about a big solar farm with storage or individual homes with storage?
Well, actually, this talk was focusing on utility scale.
Yeah, okay.
A big in other words, you have like a big solar farm, you know, that has a zillion panels, where you have all these windmills, and then you have a fairly large, maybe a building. I showed that picture in Australia of all those little battery things, and you know, they take up a fair amount of space. But you have something like that. Yeah, I mean, I think I'm slightly, we have solar panels at our house, by the way, and we have this complicated system of solar panels, and then we have geothermal energy, and we have radiant heat. So we have hot water that goes under our floors, and the way that gets hot is that the solar panels provide electricity, and then we have a heat pump that then you know, heats the water, the heat pump, driven by electricity. And so we sort of solar heat our house in this sort of indirect way. And they're great. I mean, it's great that so many people are putting panels up, I think. But I think that the economy of scale is such that we really should think more about having utilities, I mean, even communities, combine and have one central area where they collect the sun and then maybe store energy and so forth, rather than all these little separate things. It's a little less efficient. There is an economy of scale, I think. But I'm all for getting solar panels. I'm going to get an electric car next. I still have an old Toyota, but it burns gas, and I'm going to use our solar panels to charge up some electric car.
Yeah, we got a comment here that we're waiting for the batteries for home use to come down.
Yeah.
So
You know, when we lived in Colorado, near where Pat Casson and Dottie Woolham, who are on this thing, live in Miramonte, we had a lot of power outages up there. We were in the mountains, and you know, every time we got a storm, not every time, but a lot of times you get these snowstorms or something, and it would knock a tree down on a power line, and power would go out in our neighborhood, and we'd be out without power. And I always wanted to get one of those Tesla batteries that for home use. You know, they're not very big. They're you know, you can mount them on a wall or something, and they provide power for you know, 8 hours or you know, some period, generally long enough to get the power back installed.
yeah, hopefully soon we'll be at that point.
Yeah.
And then we got one final question snuck in here. What about geothermal energy? And there are variations of temperature under the ground everywhere.
Yeah. And one of my best friends, when for a while, I lived in Berkeley, California, and I worked at UC Berkeley, and it was an Argentinian who came up to study to be an astronomer like I am. And, but then there weren't any jobs in astronomy. And so he went into geothermal, and Lawrence Berkeley lab at that time had a geothermal. Now he works in Mexico, but he was telling me about, one of the keys to getting, the problem with geothermal is that you need to dig deep enough to get to the hot stuff. I mean, and of course, some places, like if you're in Calistoga in California, or if in Yellowstone, that hot stuff comes right up near the surface and it's not a problem. But in other places, you got to dig really deep. And the key would be even to get to the magma, you know. And he was telling me about these drills that they were devising where you can drill like 10 miles down with these drills. And that one of the problems was that if you start drilling that deep, the drill would start to bend and turn in a direction you didn't want, and that they were designing them, I don't know, with some sort of computer controls that they can just make them go straight down. Mm. I think there is potential in geothermal, definite potential. I mean, it's not something that I know that much more about, but yeah, yeah, geothermal getting, and then just pumping water down and getting steam out is a possibility. Yeah.
Yeah. Yeah. Well, we have a lot of other comments here. Excellent presentation, wonderful talk. I certainly think you took what could be a very complicated subject and broke it down very, very nice in layman's terms. So appreciate that. And I'll just wrap it up here. And thank you for your time, Dr. Hollenbeck. We really do appreciate it. Great talk.
It was my pleasure.
Yeah, I see the hands coming up. Okay, thanks so much, everyone. Take care, and we'll be sending feedback forms out.